All right, welcome back to the Math 1040 Lesson 20 about one sample hypothesis test for a mean. And just a really quick recap. We're going to have some hypothesis that the mean is equal to some value, an alternative that it's different in some way from that value. And the gist of it is we get an x bar from our sample, and is the difference from it to C likely random or is it likely real? So let's get into some examples. So we call it a one sample test because there's only one sample, but there's usually two population means. The mean, there's some population that has a value, and we're comparing our sample mean to that value. So there's two populations, the one that's bigger and the one that our sample represents. The mu in the hypothesis, it's already underlined, but right here, when you state your hypotheses, the mu always represents the mean value of whatever you're measuring for the population that the sample represents. The null hypothesis always specifies that the population value that our sample represents and the population value that we're comparing it to are the same. We have to assume they're not different. And the alternative always states that they are different. That's usually what we're trying to show. The claim is the alt. Last thing, there's a tip. You don't have to do this, but I'm going to attach a subscript to the given mean to keep it separate from the other mean. So that might have felt all really complicated. Hopefully the examples here put it all together. The first one's worked out for us, but let's go over it step by step. In the United States, IQ scores are normally distributed. I'm going to go ahead and underline important things. Let's not use purple. Purple's already the text below. With a mean of 100 and a standard deviation of 15. A random sample of 13 Snell College professors had a mean of IQ of 110.4. Test the claim at 1%, significance that the mean IQ score of Snell College professors is higher than the national average. So there's our claim, that's our significance. So it's helpful to write what you were told down. So this right here is going to represent the national mean IQ. So the little capital N subscript is for national. The X bar is the sample mean of Snell professors. And we're told the standard deviation is 15. So when you're just like told as a fact about some mean and standard deviation, those are going to be mu and sigma. So this is like for the general population. So this standard deviation is a sigma. And our sample size of 13, and that's our significance level of 1%. And if you read the problem carefully, it never mentioned what the standard deviation of the 13 Snell College professors was. If you read this sentence right here, it just says the sample mean. It doesn't say about the sample standard deviation. All right, so we have one sample. We're testing a mean. This is average and mean. So if we were looking at this, we're doing means. We have one sample and we know sigma. So we're in this column here, which is a one sample z-test of a mean. The requirements for this are you need to have a random sample and either 30 or higher sample, or the data is known to be normal. So we have one sample, or we're here actually. The sample's random, it says that right here, random, okay. And either the population data is normal or the sample size is 3 or higher. Only one of those needs to be true. If they're both true, that's cool too. But at least one of these two things needs to be true. And we're good. And so we're going to test the claim. Let's see. Here's a claim that the mean IQ of Snow is professors is higher. So higher is going to translate to a greater than. So down here, this becomes our claim. The claim typically becomes the alternative hypothesis. So this mu represents a different population than this mu. This mu always represents the population that the sample represents. And the sample represents Snow College professors in general here. So I wrote all this out to explain this. Since the sample is the 13 random Snow professors, the mu is the mean IQ of all, and that's important. Entire population. We don't know what that is. We didn't do the whole population. We just have 13 values. But the null hypothesis here always assumes the two values are not different. Why do I say not different? Null means nothing or no difference. This, I know it sounds weird, but same or equal. So we assume the mean of this population is the mean of the other population. Then we do our test. Since we're doing a z-test, we can use, we're here, so we can use this z-score formulation and plug in the numbers and calculate a z-score of 2.5. We're going back to blue. What does this actually mean? We would draw a normal curve, put 2.5 on it, and because the alternative has a greater than right here, greater than means go right, so we would go right, and our p-value is the shaded area on my drawing. So that's from 2.5 to infinity, or big number. And the shaded value of the area is 0.006. That's our p-value, which is the probability, if the null hypothesis was true, the probability that we saw what we saw. So this 110 is a lot more than this in terms of standard errors, basically. So the probability that we saw what we saw given the null hypothesis is true is close to 0. So that's really strong evidence that the null hypothesis is not true. The rule of thumb is if the p-value is less than or equal to alpha, we reject the null hypothesis. What does that mean? We assume that the mean of Snow College professors is 100, just like the national mean, and our claim is that it's actually more. But when we reject it, we're going to throw this idea out the window. We don't think that's true, actually. So, therefore, the other idea is probably true, which means that we have sufficient evidence at the 1% significance level that the mean IQ score of Snow College professors is greater than the national mean. The mean IQ score of all. So we used the data from 13 randomly chosen Snow College professors to test a claim about all Snow College professors. In this case, the evidence was strong enough that we can make a claim. All right, this is probably the moment that is most important. Well, I think the conclusion is most important, but as far as calculations go, I like what we do in step 5 here, doing the z-score and p-value manually, but I know most of you don't, so luckily there is a calculator shortcut for this. Oh, okay, we'll do it like this. So if you consult the table, or just remember, we're doing a z-test here. We're doing one sample, we have one sample, sigma's known. We got our hypotheses, so let's do our z-test. So in the calculator over on tests, we have its very first one, z-test. And you can actually put data in. So suppose we had those 13 IQ scores, we could put that in a list and do it right off that. But it's even easier if we already know the mean, the sample mean. We go to stats. Okay, this is our null hypothesis right here, mu0. That's why you should write it down. So I wish the calculator said h0 mu, like normally in statistics this is the way we write it down, but it just says mu0. This is the null hypothesis value though, so we assume it's 100. That's our population standard deviation. This is our sample mean, our sample size, and our alternative hypothesis is this one. So again, where do we write that down? Write it down. Make sure you put it in right. It changes everything. If you put in the different choices here will give you a different answer. And only one of them is right, the one that matches the actual claim that we're testing. Calculate. That's our z value, the same that we calculated with the formula, if you round that. And that the next one's our p-value, same that we calculated with normal CDF. So the z-test did step 5 for us, which is really handy, but it sort of loses the intuition about what's really going on. So either way, it's fine. If you do this though, check that the null hypothesis or the alternative hypothesis matches, then your z-score and your p-value, and check that the sample mean and sample size are correct. That's what the output says here. All right then. We'll do the next two examples in another video.